Okay, well, as I said earlier, he kind of goes in one direction with the definite integral. I'm going to take you a little bit different direction, and we're both going to meet at the end, but kind of a little different direction, a little different thinking procedures about how to work through these, but both ways very, very important. Today we've got a lot of kind of introductory things to do. We'll kind of lay the foundation today, and then the next couple days we'll build on top of that and finally get to the finished product in probably by Thursday. But the build up here, we're going to be dealing with what we call summations. Sometimes these are called sigma notation. We use the Greek letter sigma to represent a summation, so that's where we do that. And then we'll also be looking at approximating areas under a certain curve, and I can't write today, that's an N, under a curve given by a function, say y equals f of x, maybe x squared or square root of x plus 1, something like that. So we'll be looking at that, and that really is kind of the bulk of the work we do, which this is nothing more than algebra. Like almost everything in calculus, we do a lot of algebra, and then at the very end we do a little bit of calculus. So that's where we're heading today, and then tomorrow we'll kind of go even farther and get into the calculus side of it. Today, yeah, we'll only see what you could do in algebra. So first up, we're going to look at the summation formulas, the notation that we have, and we'll first look at this. There's the fancy little sigma. I think it's a capital sigma to be exact, but when I handwrite that, it's not going to look quite like that. But what we end up with, the I or J, or in the second case K, these are the usual letters we use for the index, or the indices, plural. But the index shows where we start, and then this shows where we end. So in this first one, we're saying we're going to calculate the sum of I squared when I goes from 1 to 5. So for our first term then, if I is 1, we'd have 1 squared. Then summation, sigma notation means, well, then we add the next term. When I is 2, we'd have 2 squared. When I is 3, we have 3 squared, and so on up until we hit our end point. Now, this is just to give you an idea of the notation, how to use it. You don't need to worry about calculating this value, but just get used to the notation. Sometimes we start with I equals 1. That's probably the most common place to start. Other common beginning points, I equals 0. We do see 0 for the starting point on many occasions. But what we've got to be careful with this one, though, where are we going to start? Okay, we start at k equals 5. So this second summation, 1 over k when k equals 5, plus 1 over k when k equals 6, plus 1 over k when k equals 7, and that's it. That's what that second summation notation means. And like I said, don't worry about trying to add all those up and get a value for it. We're working with notation right now. Questions on the notation? Now, here is a problem where we go the other direction. We've gotten the sum in expanded form, and we need to write it in the sigma or the summation notation. So as we look at this, we take a look at, well, the brackets kind of say, okay, this is going to be one term, then the next, and so on. So this will be our first term. And a lot of times in general, we say this is A sub 1. Okay. So when I equals 1, that would be this first part. Then we take a look, this would be A, or when I equals 2, A sub 2. And so on. Now we don't know how many terms there are in here, but this would be, well, in general, we might say this is A sub n. N, in this case, looks like it goes up to what? Okay, as we look at term by term here, looks like the only thing that's changing is this right here. So let's write this as a summation then. That's as good as my sigma gets. So summation as I goes from 1 to 6 of what?
7 or
Okay. And that is correct.
so I and K is the same thing?
Yeah.
Because K
Yeah.
is plural?
It's just a difference in the letter we use. Just like in equations, we usually use X, but we could use Y, we could use Z,
Just a variable?
just a variable, yeah. The most common indices are I, J, and K, but we could use others as well. So, but this would be the answer to that summation. We see the pattern that's happening, what's changing from one to the next term. That's going to be where the I shows up, and then what stays the same. Okay? So again, just kind of getting an idea what the summation, the sigma notation is going to be dealing with. Now, we use the sigma notation in our definition for the definite integral, but we have a ways to go before we get back to using that. So the next step after introducing the sigma notation, we're going to be looking at how we approximate the area under a certain curve. Now, the problems on your worksheet today will be stated like this. Well, the ones after the sigma notation. I'll throw in a few sigma notation for you. But this will be the key part. And it says use part A, left endpoints, and the part B, right endpoints. We're going to have several parts to this. Of each subinterval to approximate the area above the x-axis over the given interval and under the curve given by the graph of y equals f of x. So this is going to be the graph that we're going to deal with over the interval from x equals 0 to x equals 2. And we're going to estimate this in a few different ways. Using, okay, first of all, we'll use 4 rectangles, okay, equal width. That's going to be a key. We don't have to go equal widths, but it will be much easier if we do. And then secondly, we'll expand it to 8 rectangles, and we'll see what the more rectangles do for us. Okay. And then finally, part C we'll kind of talk about after we get through one of these. Now for my demonstration today, I will do the left endpoints and right endpoints both for n equal 4, but we'll see how much time we have. We may only do one of those for n equal 8, just time-wise, and then we'll be able to at least compare, answer part C here then. Okay, the idea is we're looking at the curve x cubed plus 1. And going from 0 to 2, and so at 0, our y value will be what?
1.
Okay, y value of 1. At 2, our y value will be what?
9.
How about 9? Plus 1. Okay, so way up here, and like normal, I probably didn't.
Wait, you did EX value too.
Yep. 2 cubed would be 8, plus 1 would be up here at 9. Okay. So my graph is probably not perfectly situated, but this will give us at least what we need to see. And the curve x cubed plus 1, well, it's going to be kind of this, goes like that, and then back up here. Now, from 0 to 2, it's probably sharper curve than that, but like normal, I didn't leave myself enough room, so we'll just have to pretend we understand that. Okay. Now, part A, we'll use left endpoints, and I'll show you what that means here as we go through this. And part A, part 1 of part A, we use n equal 4. Okay. So we're going to split this into 4 parts, and ultimately, man, I wish I could draw straight. Ultimately, we're going to be estimating the area from 0 over to 2. This nice little region here. And we can do that, well, we could do that with one really big rectangle. We could say, let's just make that one big rectangle and say the area under this curve could be represented by, what would it be? 18, width of 2, length of 9. That's not a very good approximation. We're counting all of this area up here as well. But going to 4 rectangles rather than just one, we can start to get a little more accuracy. And we'll be able to draw fairly decent rectangles, or you guys would be able to. I hope I will. What is the width of the rectangle if we go 4 rectangles over this interval?
What do you mean for? Like
We're going to split this region into 4 parts. Okay. So the width of that would be what? Okay, each rectangle would be 1/2. Now what we will find, there's a nice little formula, and oh my, there's that little delta x again. that little change in x, that's going to be our width of each little part. That's going to be the b minus a, which is the length of the interval. In general, we say we go from a to b, so 2 minus 0 over n. Well, in this case, we're saying let's let n equal 4. So 2 minus 0 over 4, 2/4 would be the 1/2. So each of these rectangles are going to be 1/2 units wide.
So that's how you find the width?
So, starting at 0, the next x value, the subinterval, as we call it, would go from 0 to 1/2. Then the next one would go from 1/2 to 1. Then 1 to 1.5, 3/2, 1.5, whatever you want to call that. And then from 3/2 on out to 2. So we've split up our region into 4 parts, 4 rectangles. And back to this point, we're going to use the left endpoints for the first portion of this. That means the length of our rectangle, or height, if you want to think of it that way, instead of going from here way up to here like we did with just the 1, we're going to use the left endpoint of each subinterval to calculate the height. The function value at that left endpoint is going to be how we calculate the height. So the first rectangle, we're going to be using 0. F of 0 is what?
1.
Okay, that's the 1. So we're going to draw in a rectangle here. That's going to be the first rectangle to help us estimate what the area is under this curve. So the area of this first rectangle would be f of 0 times delta x, which we already calculated. F of 0 is 1, delta x is 1/2. This area right here is going to be 1/2 square units. Okay. Now what about the second rectangle? We use the left endpoint of our second subinterval to calculate the length, the height. Well, that's going to be using 1/2. We come up here to the curve, and we get that rectangle to represent our second subinterval. The area of that second rectangle would be what? Okay, f of 1/2 times your width, again, times the delta x, and 1/2 plugged into our function. 1/2 cubed is 1/8, and then plus 1. 1 1/8, 9/8. 9/8 probably be easier to deal with here. And then times the width. Okay. Now the third subinterval we'll finally see a little bit better on the picture. We're kind of real close to the curve itself on these first two, but the third subinterval, left endpoint, will be 1. So a sub 3 would be calculated by doing what?
F of 1
F of 1
times the delta
times our delta x. And there's the rectangle that would represent. And f of 1 would be what?
2.
Okay. So 2 times 1/2 on that part.
That's right.
And then finally, our fourth rectangle, left endpoints again, we'll be using 3/2 this time to calculate the length. And our rectangle looks like that. Length of f of 3/2 times our width, and 3/2 cubed, 27/8 plus 1, 27 and 8,
Is that 36?
35/8. At some point, you'll be plugging these into your calculator anyway and just write a decimal. And then we add all 4 of these. And we say capital A, sometimes we represent the capital A as the exact area. Adding all of these will be approximating that exact area. And we end up with what? Someone want to plug all that in your calculator?
Yeah.
So our approximation, using 4 rectangles, using the left endpoint, we get 4.25 or 17/4. So this is fine. Just do the decimal.
So
Okay.
what about the right endpoints?
Okay, next up we'll use our right endpoints. Now, for this, we'll kind of get a little cluttered here on this graph, but just to show the comparison between the two, I want to do that. Then we'll go to the next page and draw a little more detailed one. But first of all, before we look at the right endpoints, would this approximation be more or less than the exact value? Or can we tell?
No, it's going to be less than the exact.
Okay, it's going to be less than the exact value. Why?
Because of all the space that we didn't count.
Okay, there's a bunch of space here that we don't count. And these first two, there's not a lot, but there's still a little bit that we don't count that's under the curve, but it's not inside those rectangles. So this would be what we call an underestimate. Okay, the exact value is going to be more than 4.25. Well, if we use our right endpoints now, well, I think we'll start over here on 2, the last rectangle, the fourth one. A little easier to see the difference there. So instead of using 3/2 like we did here, we're going to use 2 for the length. And that rectangle will be this way. And then the third rectangle, using the right endpoint, would be the 3/2. We have that as our third rectangle. Second rectangle will be this, and then the first rectangle will be this. Okay? Now, would the right endpoints be an overestimate or an underestimate? Okay, this time it's going to be an overestimate because we're going to be counting this space inside the rectangles, but they're above the curve. So a little extra. Okay, well, let's go to the next page and write out this. So here's our function, our graph, our rectangles. And this time, the length of the rectangle will be represented by our right endpoints, looking at these points on the curve. So A1 will be f of 1/2 times our delta x. Well, we haven't changed the size of the rectangles width-wise. We're going to have the same width. It's the height that we're changing. And, well, some of these we already calculated. F of 1/2 was what?
9/8.
That was the 9/8. And then times 1/2. A2, our second one, well, that's now using 1 as our right endpoint. That would be, oops, 2 times the width. Then f of 3/2 times delta x, and that was what, 35/8. And then finally, the fourth one calculation we haven't used yet, the right end of our interval, and 2, well, we already knew that one though, 9 times the width. So add those up, and what do we get?
33/4, or
8.25,
8.25.
okay. And this should be approximately equals. So based on those two approximations, the exact area is going to be in between 4.25 and 8.25. Okay? Okay, both approximations, both fairly decent approximations. How do we make it a better approximation?
More rectangles.
Okay, more rectangles. Well, looking at this, part 2 of each, part A and part B, says use 8 rectangles and use left endpoints, use right endpoints. And that's going to give you a closer value. Left endpoints will probably get around maybe 5 or 6, something like that. And the left endpoints, or right endpoints, I guess this is right endpoints, maybe we'll get around 6 or 7. So the range narrows in as we use more and more rectangles. Now, I'm not going to go through the all of the 8, but just kind of give you an idea what would change if we go 8 rectangles. What's delta x going to change to? Okay, 1/4. We'd still have the length 2 minus 0. 2 is the length of the x interval, and we're splitting that up into 8 parts this time. So 2 divided by 8 would give us the 1/4. Okay, so now we need to kind of expand our x values. Our first subinterval would go from 0 to 1/4. Second would go from 1/4 to 1/2. Third, 1/2 to 3/4. This is where we get really cluttered and trying to do too much on one graph. Then 1, then 1 and a fourth, 5/4, 3/2, 7/4, and then 2. So we do all of this again, except A1 using left endpoints. We'll do a couple of them here. A1 would be, well, left endpoints, we'd still be using f of 0, but then we'd be multiplying by our delta x, which is 1/4 this time. So A1, 1 times 1/4. A2, we'd have that as our height of the rectangle, f of 1/4 times delta x, and f of 1/4 cubed would be
64,
yeah,
164.
1/64 plus 1, so,
Which is gonna be 65 or 64.
and then times the 1/4 again. So it's not difficult operations, it's just long. And the reason we go through this is to show the more rectangles we have, the more accuracy we get for the approximation. Like I said earlier, with the 8, we'll have maybe 5 to 6 for the lower end and maybe 6 to 7 for the upper end. So we get a lot closer on our approximation. Yep.
What's the difference between left and right?
Okay, the left endpoints, calculating the length of the, or height of the rectangle, we do that by plugging in the x value on the left side of each subinterval. So for the 8 rectangles, we have 0, 1/4, 1/2, 3/4, 1, and so on. To calculate the length, we use f of 0. Okay. Now for the second part of it, the right endpoint, the first rectangle, we would use f of 1/4 rather than f of 0. Okay?
Till 2.
Right. So the left endpoints, you're going to stop at f of 7/4 as your length. And then the right endpoints, you'd stop at f of 2.
And then you start at 1/4.
Right.
Okay.
So, okay, that kind of gives you an idea where we're heading, and you've got a worksheet here. You'll be able to spend a little bit of time. Probably will need to spend a little bit of time tomorrow and the next day working on this as well. So.